Hello. This morning I've got another job in my shop here. It's a repair to a speed reduction gearbox shaft. This is it's actually a cast iron shaft with a bronze worm wheel on it, and it has they're not on here right now, but there's a couple of large taper roller bearings, and then this surface and this surface are the sealing surface to keep the oil in the gearbox. This gearbox is used on essentially a welding positioner for a company that makes large welded frames, and this gearbox allows them to rotate the frame to different positions so that they can the guys can reach it to weld. One of the things is that one of the issues they have with these is that in order to rotate it really slow, they have to have a very large speed reduction. So they actually attach a second smaller gearbox to the input shaft of this gearbox, and then they run the whole thing with a small hydraulic motor. The end result is you get a 1200 to 1 speed reduction, which causes a massive increase in torque. And that torque isn't necessarily needed for the job. It's just a side effect of having the shaft turn so slowly, which is what they want. They want this to, I think this thing turns at around 1 RPM, which is perfect for when you're trying to position something for welding. The shaft, it's a 3-inch diameter shaft, passes through this shaft, and at the end of that shaft they have a locking plate, which is also which is mounted to the shaft, and there's 4 holes in it every 90 degrees, and you can put I think it's about a 1-inch diameter pin in, and then that locks the thing solid so that it can't rotate when the guys are in the frame welding. The problem is often they don't pull the pin out. I shouldn't say often, but once in a while they forget to pull the pin out, and then they go to rotate the frame. And because this thing has so much torque, it'll bend the pin and damage the locking frame. It'll also, if there's what's called a taper lock is used in the end of this shaft, and it can overcome the friction in the taper lock and cause it to rotate, to break loose, and it'll shear the mounting bolts off. It'll sometimes, this is a cast iron shaft, and it'll sometimes crack it. That's what's happened in this case. This one was cracked here, and so they've welded it up, and then they asked me to machine that down and then reestablish new holes, because these holes are beyond repair. Well, they might be able to be repaired with a helicoil or something like that, but it's really just easier to move the pattern over and redo it in the end of the shaft. So that's what my job is today. This shaft uses, I mentioned before, taper locks. QD taper locks are called, and I'm sure a lot of you are familiar with them. For those of you who aren't, it's a method of mounting a shaft into a pulley or a sheave wheel, and it makes for a really tight joint. Instead of just boring a pulley out to fit the shaft and having a very tiny amount of clearance, you put these in, and they actually crush down on the shaft and eliminate all clearance. And the way they work is they have a bore through the middle that's sized for the shaft you want to use. They have a keyway, so you can put a key in between this and the shaft, but then this diameter is tapered, and then the mating part that this is going into, whether it's a pulley or a sprocket, has the female taper in it, and it has 3 holes, threaded holes in the end of the shaft. So you put the shaft in here with the key, and then you put this in the pulley, and when you this is my fingers are the end of the shaft. As you draw this in the bolts, this crushes in because of the taper, and it removes all the clearance here. It's split so it can move in almost like a collet, and it removes all clearance and makes a very stiff joint. Now, normally when you use these, you're just using a single one in a pulley, and that makes it pretty easy if you have to machine the pulley, say, because you if you have to put the bolt pattern in the pulley, you just put the 3 holes in 120 degrees apart at the right bolt circle diameter, and that's it, you're done. On this shaft that I'm doing today, there's an added complication, and that complication is that there's a taper lock in each end, and those taper locks join to a common shaft, a 3-inch diameter shaft that passes right through this shaft. So what happens is you have to put a bolt circle pattern on this end, and then you have to put one on the other end, and they have to be related to each other. Otherwise they'll be out of position like this. They'll be out of position rotationally, and because there's a keyway, they won't work, because these two are going to face each other like this. We can see the keyways when we line them up. In order to have those keyways lined up, the bolt pattern on each end needs to be positioned correctly on each end, and it makes it a bit complicated, because the end you want to clock off of is down on the milling machine table. It makes it difficult, because in order to establish the circle on this side, you need to go off the circle on this side, and it's down on the milling machine table. You don't have any access to it to measure it. This is the first end I'm going to do, so I have a bit of free rein on where I put the holes to a certain extent. But once those are in place, then when I go to do the other end, I have to accurately go off of this pattern. Now, originally when I looked at this, I thought these holes are 120 degrees apart because there's 3 of them. And I thought, well, I'll just shift the whole pattern 60 degrees and put the holes between these 2. There's a problem with that, though. And the problem is that these taper locks don't just have 3 holes in them, they have 6. The through holes are used for the bolts to draw this down. The other holes are threaded, and they're jacking screws for when you want to remove this taper lock from the bore. You unscrew the bolts out of here and you put them in here, and you screw down, and it pries this out of the end of the shaft. The issue is, if I simply put my pattern halfway in between, then the jacking screws line up with the old holes, and they're not going to have anything to jack against. They're going to go in here, and it's going to be really half-assed, and it'll probably damage the thread, and might damage the shaft, and it'll get crooked, and it'll just be no good, to put it politely. So what I have to do is shift the pattern over 30 degrees, and you can see I did that here. I just marked it, and this mark here is an old jacking screw mark, which is helpful because that shows me the position. There's where the bolt goes, there's where the jacking screw is, so I want to move the threaded bolt hole halfway between those 2 positions. So I just took a ruler and measured and got halfway. I don't have to be really accurate in establishing this new pattern on the first side. As long as I'm roughly 30 degrees over, that's good enough. The pattern itself will be accurate. And then when I flip this over and do the second pattern on the other side, that has to be done accurately relative to this. But the initial hole doesn't have to be placed all that accurately. So there's one other complication with this too, and that is that when you turn these so that they face each other and the two keys are lined up the way they're going to be assembled. Let's see if I can do this so you can see that. If you look, you have a through hole here for the bolt to draw it in, and directly across from that is a jacking screw. So by turning them and facing each other, the whole pattern shifts 60 degrees. So it's another complication. Not only do I have to clock off the bottom of the shaft, but then I have to remember that I have to shift the pattern out as well. So it's just something you got to keep clear in your head when you're doing it, so you don't bugger it up. There's not a lot of real estate left on the end of these shafts, with they're already having one set of holes, so you want to make sure you do it properly the first time. So I've got it mounted. I stoned these faces down to make sure they're flat. I got it mounted to the table. I just need to pick up the center now, and then I have a bolt circle function in my digital readouts. So to position the spindle in the center of the shaft, I've got a Blake coax indicator, and I'm just going to use that. The way these work, you spin them with the machine and you strain them with the arm, and then it frees up both your hands. You can put one on the y-axis, one on the x-axis, and then you essentially adjust the x and y axis until the needle stops swinging back and forth. See, you can see there it's moving just a tiny bit, but that's only a few tenths. So we're in the center, and then we'll just zero this so I know where I am. Zero everything in case I screw it up. The way this works, you essentially enter the diameter. Not sure of the order, but the diameter of the bolt circle, the number of holes, and the angle to the first hole. And if you put, I believe the way it works, I haven't done this in a while, but I believe if you leave the angle at 0, it puts the first hole here, straight across to the right from the center. And then if that's not where you want it, if you want it somewhere else, you have to enter the angle, and I think the angle increases as you go counterclockwise. So I want this to be my first hole, so I believe I have to go 270 degrees. But it's easy enough to check. You just enter that in, select first hole, and see if it puts you in the right direction. So now the bolt circle diameter, I printed off some information from Martin, the manufacturer, and they have all the dimensions here. So it's an E-style taper lock. So we find that, and then we just go across where it says bolt circle, and the diameter is 5 inches. And I've checked that with a ruler just to see, and it is 5 inches, so I know that's correct. You select this that looks like 4 bolts on a circle, 4 bolt holes on a circle. There, and it prompts you to put the diameter in, so 5 inches. And then N is the number of holes, so that's just 3. And then the angle to the first hole, I'm going to put 270, but I'm not sure. We'll see. And then what you do is you just press load, and it comes up and says 1 of 3, and there. So 2.5 inches in the Y direction, which I think is, nope, I got that exactly backwards. See, I'm moving towards where I want to go, and the number's not heading towards 0. So what I need to do is just cancel out of bolt circle, and then I'll go back to the 0, 0 position, which is the center of the shaft. And then I'll just re-enter the information. So it's 5 inches, that's correct, 3 holes. Oh, whoops, sorry. Yes, 3 holes. Angle to the first hole, I'm gonna go 90. I guess it must go the other way. And we'll see what happens. And then load the first hole, 2.5. I'm heading towards where I want to go. The number's getting smaller. And when I get to 0, I should be right over where I want to be. And you can see I'm not perfectly in line with the marker mark, but as I said before, I don't have to be that accurate when I'm establishing this first pattern. And you just press load, hole 2 of 3, and it puts 2 new numbers there. And then you just, again, if I wasn't holding the camera, I'd be running both axes at the same time. It'd be a little bit quicker, but it's okay. Just go to 0 on that one. And 0 on this one. And you can see we're over here. And you can see we got one here, one here. Looks like it's about 120 degrees. Spot that one and just repeat. And there we have hole 3 of 3. And we just go straight across. Now I measured the old holes and they're approximately 1 3/4 deep. So I'm just gonna go to the same depth, and to do that I have a quill kit, I believe they're called. It's just like a small digital readout for the quill, which makes drilling holes to depth very handy, and also very handy for counter boring. I'm going to tap these by hand, not under power, because the hole is fairly deep and the part is very expensive, and I'm not very good at getting broken taps out of holes, so I like to just not break taps in the first place. I'll switch from a starting tap to a plug tap. Sorry, I think this is a bottoming tap. Bottom. I'll just run her down one more time and make sure. Cast iron is quite easy to tap, and the nice thing is that the as the chips are formed, they just fall out of the tap down the hole, so they don't plug the flutes until you get right to the bottom of the hole. But for most of it, it's pretty good. Okay, that's the bottom. Of course, this is one of the bolts that came with a taper lock, so we'll just make sure it goes in. And there should be about, yeah, it's pretty close. There's about 5/8 of thread. So the thread is about 1 5/8 deep, which is probably correct. I measured the holes as 1 3/4 deep, but that was right to the point of the drill, at the very bottom of the hole in the point. So obviously the threads aren't going to go all the way there. So that should be deep enough. That should be good. Okay, so the holes on the first end are complete. It drilled, tapped, and chamfered. Now I have to come up with a way to position these holes on the table so I can clock off them when I'm going to do the other end.